Okay, now we will get to the question of assigning coordinate frames to each link. Okay, because we already discussed this, that a coordinate frame is attached to each link, but how that coordinate frame is attached. Okay, we are going to discuss that here. For that, few terms are defined here. One is joint axis. Okay, joint axis is the axis with respect to which the motion of joint is described. So here you see there is a revolute pair between these two links, and joint axis, we call that as z axis, that will be the axis of rotation here. Okay, because that is the axis for which the rotation theta, along that axis will be the rotation theta for the joint to describe the motion. Right hand side you see a prismatic pair here, and now the joint axis is this. Okay, you see here, because that is the direction along which the motion is described. It is a sliding motion, so those are joint axes. Okay, now let us talk about numbering of links, joint and axis. So here we have a robotic manipulator, and links are numbered starting from 0. So you have here, those are not numbered starting from 1. Those are labeled as link 0, link 1, link 2, link 3, and so on. Okay, and corresponding to each link there will be a coordinate frame. So you have 0 written within this curly bracket, so that means this is frame 0, frame 1 which is attached to link 1, frame 2, frame 3, so like that. Okay, those are the links and frames. And joints are labeled starting from 1. So this is the first joint. This will be called joint number 1. Then you have joint number 2, joint number 3. And axes are labeled starting from 0. So this will be axis 0, axis 1, axis 2. It is important to remember this because uh, when we are assigning coordinate frames to the link, we are going to use some index, say axis I minus 1. Okay, so then it becomes important to understand how axes are labeled. Otherwise you will wrongly understand which one is I, which one is I minus 1. Okay, so look at this again. So if you are looking at link number 2 here, okay, link number 2 will be between joint 2 and joint 3. Okay, but will be between axis 1 and axis 2. Okay, that is how this numbering is done. Okay, now first let us talk about what are called link parameters. And link parameters are constant for a given link. They don't change. So this figure is not very clear here. I'll actually, it will be clear in your notes, but in recording it may not be so clear. Here you see a link which is just a twisted link, and you can think of it has two revolute pairs. Okay, so this is called link number I. It has two revolute pairs, and the axes are, I already described you what the previously we saw what the joint axes are. So corresponding to these pairs or these joints, okay, these are the axes. This is one axis. This axis is called axis I minus 1. Okay, that is how they are labeled. This one on the right hand side, this is called axis I. Okay, so we have link I, axis I minus 1, axis I. Okay, now based on this, how link length is described. Link length, it is called AI. Okay, that is the notation used. It is actually the perpendicular distance to both of these axes. Okay, so you have this axis I minus 1, axis I. Draw a common perpendicular. Here you see that common perpendicular is this AB, and its length AI, that will be called the link length. Okay, so even though link moves, but it is clear that this is not going to change because relative orientation and position of axis I minus 1 and axis I will not change. Okay, so it remains fixed. So that is link length. And what is link twist? Link twist is angle between axis I minus 1 and axis I. Okay, and this is indicated as alpha I. So you see axis I minus 1 is along this direction, axis I is along this direction. There is an angle between them. So you can think of it like this. You can actually move axis I minus 1 to point B. Okay, and then see what is the angle between I minus 1 and I, because they will be at the same point now. Or move axis I to point A and then see what is the angle between them. Okay, so that is called link twist. But one question arises, how to measure them. There has to be a sense, because it could be, for example, link twist could be 20 degree or minus 20 degree. So how to measure that, we'll look at that later on. But corresponding to a link, you have these two parameters, link length and link twist, which are constant for a given link. So as an example, you see here another link I, and this is axis I minus 1. This is indicated as Z I minus 1. This is axis I, indicated as Z I. Okay, the common perpendicular to these two axes is this distance here, that is AI. And in this particular case, you see the twist is actually 90 degree. Okay, that will be the angle between Zi minus 1 and Zi, that will be 90 degree. So that is link twist here, just an example. So those were link parameters. Now let us look at joint parameters. So for joint parameters, we have to look at a joint. So you see here link I minus 1 and link I, and there is a joint here between them. The joint is joint I. The axis through that will be axis I minus 1. So this is Z I minus 1. On the left hand side you see Z I minus 2, and right hand side you see Zi. Okay, so this will be the arrangement that describes actually two links connected by a joint. And now what are the joint parameters? There are two joint parameters. One is joint distance and other is joint angle. And these parameters are not constant. Okay, if they are constant, that means there is no motion at the joint. Depending on the type of joint, one of these two will change. If it is a revolute pair or revolute joint, then the joint angle will change when motion occurs. If it is a prismatic pair, then joint distance will change. Okay, so those are not constant, but let us see how they are defined. So first, let us, in this figure we can also look at link lengths. So here you see there is a common perpendicular between axis I minus 2 and axis I minus 1, which were the two axes for link I minus 1. And this distance will be called AI minus 1, that is link length for link I minus 1. Okay. Similarly, you have here AI, that is link length for link I. Okay. And now there are two more things here. You see, one is this angle theta I, and one is this distance di. Okay, these two are called, this theta I is called joint angle, and di is called joint distance. And just based on the figure, I hope you get a sense. If it is a revolute pair, there is going to be rotation about axis I minus 1, and based on that, this angle theta I. See, what is this angle theta I? Theta I is angle between this AI minus 1, this direction, and AI direction. Okay, direction of these two. That angle is theta I. So if there is a rotation at this joint, along axis I minus 1, then theta I will change. Okay. And if there is sliding along this, then this di will change. Okay, di is the distance along axis Zi minus 1. Okay, from this AI minus 1 line to this AI line. Okay, this distance, this will change. Okay, so you get a sense here. The formal definition of these two are di, which is called joint distance. This is the perpendicular distance between two adjacent common normals, AI minus 1 and AI, measured along axis I minus 1. Okay, that is what it is. It is perpendicular distance between two adjacent common normals. So two adjacent common normals are these ai minus 1 and ai. Okay, and perpendicular distance between them, see this axis is perpendicular to both of them, this is perpendicular distance between them, and it is measured along axis I minus 1, and it changes for prismatic pair. I already described that. So that parameter is called joint distance. It is a joint parameter. And joint angle theta I, this is the angle between two adjacent common normals ai minus 1 and ai, measured in right-handed direction about axis I minus 1. Okay, so it also tells you how it has to be measured. So axis I minus 1 here was in the vertically upward direction. So angle between ai minus 1 and ai measured along this direction. Okay, that is this theta I or joint angle. So these two are joint parameters. So we talked about link parameters and joint uh, uh, link parameters and joint parameters. Now joint variable for revolute pair is theta I, because for a revolute pair theta I is what changes, that is joint variable, and joint variable for a prismatic pair is di, that is what changes. Now, having described joint parameters and link parameters, let us talk about what is called Denavit Hartenberg notation. Okay, this notation is a systematic procedure for assigning right-handed coordinate frames to each link. See, that is the topic we are talking about, how to assign coordinate frames to each link. And for that, there is a systematic procedure uh, and notation that is called Denavit Hartenberg notation. And I have written, let us see, I have written some steps here, and you will also have to refer to figure 3.8 from book. And then there are 4 Denavit Hartenberg parameters, the link parameters and joint parameters. We'll also see how those are defined. Okay, so let us go through this. So the procedure is frame I is attached to link I, okay, at distal end and moves with it. So distal end means, actually, let us go through some figure. Okay, so we go through this. So this is link 2. Frame 2 will be attached to link number 2. Okay, and frame 2 will move with link 2, and frame 2 is attached uh, around the distal means which is away from the base. Okay, so this end here, this is away from the base, this will be called the distal end of link 2. So the coordinate frame 2, actually it will not be assigned at this point, but it will be assigned in this region. Okay, you understand that in this way, at distal end of that of link I, you are going to assign coordinate frame I. Okay, now zi first, so we'll have to see assign xi, yi and zi. Okay, when we have done that, we'll also have the origin and we'll have the coordinate frame I assigned. So first of all, we assigned zi, and it is aligned with axis I, so it is straightforward. We already have joint axis based on the joints, and zi will be assigned along the along axis I. Okay, straightforward. Okay, now xi will be assigned perpendicular to zi minus 1 and zi. Okay, and it points away from zi minus 1. We'll look at this. I'll refer to figure 3.8 and explain this. Okay, so zi is straightforward. Xi will be perpendicular to these two. So xi will be actually along ai. That was the joint, not the joint, that was the link length. Xi is just along that. Okay, it is perpendicular to the two axes for that particular link. And once we have xi and zi, we get the origin. Origin will be at intersection of xi and zi, straightforward. And then yi, that is also straightforward. This will be based on right-handed coordinate system. If you have x and z, based on right-handed system, you get yi perpendicular to x and z, and you also get the sense of yi. So let us refer to this figure 3.8 in the book and go through this. Yeah, okay, so this is the figure. uh, so there is link I minus 1, link I, x is I minus 1, x is I minus 2. This, let us look at assignment of frame I here. Okay, it will be assigned at the distal end of link I. Okay, first of all, you assign zi, that will be just along this axis I. So very straightforward. So zi is along this. Okay, then xi will be along ai. So you have this common perpendicular. This is perpendicular to zi minus 1 and zi, and along this direction pointing away from zi minus 1. Okay, this will be xi, and once you have xi and zi, you will also get yi. Okay, so this is coordinate frame I here. We don't need, when we are doing the problems, we don't need yi generally. So just showing xi and zi is sufficient. This is coordinate frame I. It looks, it is not on link I here, but actually it is attached to the link. As link I moves, this moves along with that. Okay, similarly you can see here frame I minus 1 here. Okay, frame I minus 1, for that zi minus 1 is along this axis, xi minus 1 will be along this common perpendicular. Okay, so this becomes the origin. So this frame I minus 1, this is attached to link I minus 1. Okay, so that is the way coordinate frames are assigned. This is called actually Denavit Hartenberg method. And there are, after this assignment, there are 4 Denavit Hartenberg parameters. Those are nothing but what we already talked about: link parameters ai and alpha I, and joint parameters di and theta I. And now there is a formal definition of these 4 here based on the coordinate systems that we have assigned. We have assigned coordinate frame I and I minus 1. Okay, you saw we have assigned I and I minus 1. Now we can have a definition of a, d, alpha and theta based on these coordinate frames. So ai is the distance along xi axis from intersection of xi with zi minus 1 to origin of I. Okay, you'll have to read it and explain it to yourself with respect to that figure a few times, so you'll get it. So I'm not reading that but leaving that to you. Refer to that figure and go through this and fix in your mind, okay, how these dh parameters are defined. Okay, now at this point we have assigned a coordinate system to each link based on this Denavit Hartenberg notation. Okay, so that was one part of the problem. And the second is, then we need a transformation from frame I minus 1 to frame I. We should be able to describe that. Okay, previously we saw that we have if we have a rotated and a translated frame, then we can write a transformation matrix, okay, for mapping from one frame to another. Now we have here frame I and frame I minus 1. Okay, so we need a matrix that can describe the mapping, and what that matrix should use is only these parameters that we have: ai, di, theta I, alpha I. Okay, because if you see, b is the origin of frame I minus 1, d is the origin of frame I, and in going from b to d, from this frame to that frame, what is happening is origin is translated by distance di in direction along this zi minus 1, and it is translated by ai along direction xi. Okay, so that is the translation, and it is also rotated by angle theta I theta I, if we measure it along zi minus 1 direction by along theta I, and further it is also rotated by angle alpha I. Okay, so that is clear from this figure that between frame I minus 1 and frame I there is a translation which is described by A and D, and there is a rotation which is described by theta and alpha. Okay, so we should be able to write a mapping based on these four parameters. So let us look at that. So we can think of this transformation in 4 steps or in 2 steps. So let us see if you want to look at it in 4 steps. In going from I minus 1 to I, what is happening is there is rotation by angle theta I about z I minus 1. Okay, you see here that that if you rotate by angle theta I, okay, let us go to another figure here. Yeah, this figure describes that. Okay, you can first think of a rotation by an angle theta I, then a translation by distance di along zi minus 1. Okay, so that translation like this. So you will reach this point and you'll have actually, you'll end up with this coordinate system 1 dash. Okay, it has been rotated by angle theta I and translated by distance di. You'll end up with 1 dash, sorry, I dash. From I minus 1 you'll end up with I dash. And then in going from I dash to I, you can think of 2 more steps. One is translation along xi by distance ai. Okay, you reach from point C to point D. Okay, and then one more step which is rotation about xi by angle alpha I. Rotation about xi by angle alpha I. So you will end up with this frame I. Okay, so we see that we are able to reach from I minus 1 to I by these translations and rotations, these 4 steps. Okay, and we can write a mapping for each of these transformations and then use the matrix multiplication to get the overall transformation. Okay, or we can think of just 2 steps. Those 2 steps will be okay, what is this? I have not written it clear. Okay, this I minus 1 to I dash. Okay, that is one step. Going from I minus 1 to I dash, and this includes the rotation and translation, theta I and di. You see that in this figure. In going from I minus 1 to I dash, okay, rotation theta I and translation di. That is one step. And then in going from I dash to I, you have again a translation and rotation of ai and alpha I. So you can think of it as 2 steps. And we can write those transformation, those mapping matrices. One will be I minus 1 t I dash, and other will be from I dash to I. Okay, and so because, and this is matrix multiplication, and if you multiply those two matrices, then see this I dash and I dash will cancel. You will get I minus 1 ti. So that will be the mapping from frame I minus 1 to I. That is what we want. We have attached a frame I minus 1. We have a frame I and we want a mapping between them. So you'll get that. Okay. And now this I minus 1 t I dash, this will be based on rotation theta I and translation di. And that matrix becomes just this one. Okay, we already talked about that 4 by 4 matrix. For translated and rotated frames, that's all it okay, based on that this has been written I minus 1 ti dash. And similarly you can write this I dash ti based on ai and alpha I. Okay, you'll get this matrix. And then this I minus 1 ti you will get by multiplying these two matrices, and their order is important. Their order has to be this. You cannot switch the order, then it will be a different thing. So you multiply them and you end up with this matrix. Okay, so see, now what we have discussed is that we attach a coordinate frame to each link. Okay, coordinate frame I is attached to link I minus 1 is attached to link I minus 1. How it is attached, we talked about that. Now having attached the links, then we have these four parameters. We have to identify those parameters: a, alpha, d, and theta. Those are Denavit Hartenberg parameters. And once we have those parameters, we can write the mapping from I minus 1 to I in this way. Okay, here c theta I just means cos theta I. Okay, so that gives us the mapping from I minus 1 to I. Now let us look at the whole manipulator transformation matrix. Now we have frame 0 attached to the base, frame 1, frame 2, and so on. We have frame n attached to, let us say, the end effector. Okay, and on the end effector there is a point of interest, point P, and we have the description of point P in frame n. Okay, so we have attached all these frames based on that Denavit Hartenberg procedure, and we have description of point P in frame n. Okay, that is easy because point P, the description of point P in frame n does not change because frame n is attached to end effector, point P is on end effector. So given np, what we are interested in, what will be P0, description of P in uh, in the base frame, which is attached to the lab, you can say. Okay, so what the transformation we are looking for is this 0tn. If you multiply this pn with 0tn, this n and n cancel, you get p0, and this 0tn will be just 0t1, 1t2, so on up to n minus 1tn. Okay, so we already wrote this transformation I minus 1ti. So you if I is 1, okay, you get 0t1. Okay, correspondingly you have this matrix based on those dh parameters. You have 1t2, 2t3, so like that you have all those, and we just multiply them, so we get this transformation matrix for the entire manipulator, robotic manipulator. Okay, so that's what we are interested in. And now we have this transformation matrix, and if we have description of P in n, we can get the description of P in coordinate frame 0, the base frame. So that is the forward kinematic problem. Okay, forward kinematic problem. So yeah, that actually ends this topic, and I'm going to stop it and continue in the next session.